Good morning. Let's get started. So yeah, today we're doing communication primitives. But so everybody knows that we have an exam on Monday. Are people okay? Are there any questions about it? No, it will include up to and including prefix sums. This is just this will help you in the programming assignment. But yes.
So, how much of existing algorithms would it include versus like just applying them to solve it?
Just the it's not about the existing algorithms that I taught. It's about like the techniques for analysis mostly. Like you won't have to remember like any of the specific applications for prefix sum. It'll just be like like if you looked at the homework for the prefix sum, just kind of like that. Like I didn't in the homework. It's not asking like how would you use the specific applications in class. It's more like how do you get this thing that's shaped like parallel prefix into the correct form. Yeah, does that make sense? Okay. And I think I said it in the announcement, but you can bring like a regular sheet and you just fill it with whatever you like. So it's closed notes, but you can write whatever reminders you want. It can be like front and back. Any other questions? So it will be starting from the beginning, like from analysis of like efficiency and stuff through prefix sums. So work span analysis, efficiency, scalability, prefix sums, and caching. Pretty much it, I think. Yeah, and so we'll try to start as close to 8 as possible. So probably we need 5 minutes to get everybody in order. So if you're in the 4220 section, please try to sit in the front, and then the 6220 folks can sit in the back so we can be better organized when we get here. Because there's a class right after this, so we want to maximize our time. Yes. Yes. Yeah. They'll be similar, but the master's one will be a little bit harder, or grad school one will be a little bit harder. And it's not that hard. I don't know. I uploaded like a lot of previous exams, so you can take a look for like the general level of what this class has been in the past. And then I uploaded some from a different class, not at Georgia Tech, but that involves some of the topics. Like previously, this class didn't include like work span analysis, for example. So there are no practice questions from Georgia Tech on that. So I included like some other exams from that. So you can look, and if you have any questions, you can like ask them on that discussion. And I think most of them have solutions too. So yeah, and the solutions for the homework 2 are out. They're not graded yet, of course, but you can check the solutions to see how it went. Good. Questions? Great. Yeah. And if you do the practice problems, you can, of course, like come to the office hours if you have any questions as well. Great. Okay, thank you. Let's start. Yeah, I know last time we didn't finish the last prefix sums example. So just to clarify, that exact application will not be on the exam, but because it's like pretty advanced. But it was a nice example. So if we have time at the end, we can finish it. But I wanted to get through this first because this is more what we need to do. It's not like only like 2 minutes of this is necessary to do the programming assignment, but most of this will be necessary for like the future programming assignments and the future exams. Yeah, so today we're doing communication primitives, which are building blocks for distributed memory algorithms. And also shared memory algorithms, and sometimes, like the general ideas are there in shared memory as well. Yeah, so like I said, communication primitives are just basic building blocks for algorithms that involve communication, which is sending data. So this is not the actual, almost all of it is not the part where you're actually doing the computation on the data. Like for example, in the programming assignment, the first local part where you have to like compute your n over p points in the beginning is not a communication primitive. That's just local computation. And that depends on the algorithm. But the communication primitive is like the part where you send the data between the ranks, like at the very end. And that is like a basic thing that can be shared across algorithms. So it's like a higher level construct. And sometimes they can include a very small amount of computation, like a reduction, for example, or a scan, like a parallel prefix, but not more than that. Like again, like the local computation of points is not a primitive. So this is one example of a communication primitive. It's called broadcast. And the way it works is that in this example, there's 4 processors, and P0 is called the root, and it has some data like yellow, blue, green, red, and it's sending all of this data that it's trying to broadcast to every processor. So there are communication primitives, and for all the communication primitives I'll talk about today, there's an MPI API for it, but we'll talk about the exact MPI API next lecture, just to make it less confusing, but these are high-level constructs that are across programming languages. Okay, so broadcast is maybe the most simple primitive, so we can start there. And the way it works, like I said, the root has some data that it wants to send to everybody. And we want to make an efficient algorithm for broadcast because we want our algorithms to be fast. And so like in this example, we have 8 processors, and processor 0 is the root, and it starts with the data. So I think we've gone through something like this before, but we'll just start here again. Like, of course, one algorithm is that processor 1 or processor 0 can just send individually the data to every processor, but that's not efficient because it serializes the communication. So basically what is going to happen is that the work of sharing the data across all the processors is going to be, it's going to be like in a tree, basically. So processor 0 sends the data in the beginning, and like these are the time steps on the Y. And so processor 0 sends to processor 4, 3, I guess, because it's 0 indexed, but 4. And then, oh, this should actually, the previous one should have been this, but I will fix it. So it doesn't really matter. Like, it doesn't actually matter what, it could be either this one or this one. Like, this is just one example of how you do broadcast. But the general idea is that, like, now that this processor has the data, it can also share in the work of the broadcast. So now the data is here, and the data can be shared now by 4 processors. So in each step, the number of processors with the data is exponentially increasing. So the number of total time, like the total number of rounds that this is going to take is log p, because we have 2 processors. Yeah. And in this example, it's from the most significant bit to the least significant bit, but it could be the other way around. And what I mean by that is the way it works is that you flip the, like this is 0, 0, 0, and then the first step is 1, 0, 0. So you flip the top bit to get who you're going to send it to. And in the next round, you like walk forward 1 bit. So instead of the leftmost bit, now you're investigating the second to left or second to right, because there's only 3 in this case. And then you flip that to get who you're going to send it to. So everybody with 0 in the middle bit is going to send to 0, or is going to send to 1 in the middle bit. And so on. Again, with the least significant bit, you just flip the bit to tell who is sending and who is receiving. Yeah. And given a message size m, which is like the number of bytes that you're going to send, the runtime, there are log p rounds. So this is tau log p, which is the latency, and mu m times log p. The message size is m. The bandwidth here, the bandwidth is like in seconds per byte to get the units right, and log p is the height. So in every round, every processor that is sending m, but they're all happening in parallel. So that's why it's not like exponentially increasing on the right side. It's just m in every round. That make sense?
So it's like the height log
Yes. So in every level of this tree, you have to send m bytes. The processors that are sending m bytes, but they're all sending in parallel, and they're not sending to the same one. In this performance model, like every processor can send or receive 1 byte at every tick in the. Yes, yeah, they're sending the same amount of data, and they're sending the same data. Like one is not getting rid of the data for the broadcast, one is just keeping it and copying it over onto 4, and then same for the other ones down. Yeah, so that's tau log p because the latency of like starting up the communication is tau, and we have to incur the tau every time because you have to wait until the data gets here to keep sending it again from 4. And it's mu m because then like once you have started the cost, then you just keep sending it across bandwidth. Yes.
So you said that the latency every communication, like if you do a bunch of time packets, each one of those is going to have a tau.
Yeah, each one of them does have a tau, but you only incur this. It's like when you send one, you don't have to wait for the one to be received. When you send the first one, you don't have to wait for the first one to be received to start sending the other one. They're kind of like, they can be pipelined. Yeah. So the upfront, this tau is just like how long does it take to get the first packet there, and after that they're all going. The question. Yes.
So, but like, don't we actually have to wait for, so let's say we go from the first level to the second level. Do we have to wait for the process to receive the packet before we start sending them?
Yes. So 4 has to receive all the packets from 0 before it keeps going.
Okay, so then we need to add the, I think
Yeah. So this is why it's tau log p, because 4 has to wait from everything from 0 to keep passing the data along, and that has to happen for every sender in every level.
So it's like the runtime, just like I don't really get like why you
Um,
like the
because that's the, like, there's some time from when 0 sends the first packet to 4 that no data is received on 4 yet, because you have to wait for the latency. But after that, like when the second packet, 0 can start sending packets just like along the wire, and it doesn't have to wait for tau to send the next packet. So like this is saying how much time does it take for all the data to get across all the processors.
so it's just like just one packet. You don't
Yeah.
need to consider like all packets that are like reach the final destination.
The second term is for all the packets to reach the final destination. Like, so if you look at one level, let's just say from 0 to 4, it takes tau to get the first packet there,
Yeah.
right? And then it takes mu m to get the remaining data there, because then you're using the bandwidth to send the packets. Like the bandwidth is in gigabytes per second. So that's saying like if you have x, so the second part is saying like if you have x bytes, m bytes to send, and you can send them mu gigabytes per second, like how many seconds is it going to take? For convenience, like we can flip. You want like how many seconds? So for convenience, you flip the bandwidth because you want to get the units right. And so that's like, so the time that you send just from A to B is tau plus mu m. And then you have to repeat that log p times. And that's why it's times log p. That make sense? Yes.
do we also want to add like the number of processors at the end, because like you're just playing with message length, but there are also p processors, so wouldn't it be like p times n as well? Like mu times it's like mu times m times p.
Like in the second part?
Yeah.
It's just, you don't multiply by p because all the communications are happening in parallel.
But the message we're transferring, like in general, we're transferring like some like a factor of p packets, right? So that wouldn't the message length be larger?
Like 0, for example, is always sending m packets every round, and 4 is always sending m packets every round after it gets in.
Oh,
And so on. Yeah. Like the amount of data that every individual process has to send is not increasing. Just the total volume of data that is being sent is increasing. But the computation or the cost model is that every processor can send and receive one packet like at every tick in some sense. So as long as you're sending and receiving, as long as there's no like overlap between sender and receivers, then you can send as many as you want in parallel. Make sense? Cool. Thank you. Questions? Are people good? Yeah. So how do we tell which processors like how do you actually do the bit manipulation to do the processors? In this example, let's say p equals to 8. There's, like I said, in the first step you send from 0 to 4. It doesn't exactly have to be this way. Like you could do it in reverse. There's nothing magic about doing it most significant at least significant, but it's simple that way. So in the first step, like 0 sends to 4. And you can't just send from all the processors with 0 in the highest bit, because then that would be not everybody with 0 in the highest bit has the data that you need in the beginning. So actually what happens is like you look at the highest bit that is sent, but you have to make sure that the lower bits are all 0, because the root is 0, so you know that 0 has the data, and then you send to 1 0 0, because 1 is if you flip the top bit in here and it matches it in the lower bits 0 0. Yeah, and you can flip the bit with XOR, like you shift over 1 and then you do an XOR. Yeah, so like I said, to get the bit to flip, you shift over, and then you also want to check if the lower bits are 0. And to do that, you get a bit mask with 1s off the bottom, and to get that, you do left shift by however many you want, or more than +1 however many you want, and then you subtract 1. So Actually, no, exactly how many you want. Like if you had 1 here and then you left shift 2 and you subtract 1, you get 2 ones. So it's not even -1 on how many you want. Yeah, so you take this bit mask with and then if you just and it with the bottom bits, if you come up with anything besides 0, then you know that that's not a candidate for sending in this round because the lower bits were not 0. And then in round 2, 0 has the data still, and now we're looking at the middle bit. So we do the same thing, like we've just flipped the middle bit for 0, 0, 0 to 0, 1, 0. And then same for here, we flip the middle bit from 1, 0, 0 to 1, 1, 0. And the lower bit again has to be 0 because not everybody with 0 in the lowest bit, or people that don't have 1 or people that don't have 0 in the lowest don't have the data yet because of the way that we sent. Like we just sent 2 ones with 0 in the lower bit, so how could 1 in the lower bit have the data? Yeah, does that make sense? Okay, so this is just the pseudocode for doing this broadcast. Remember, like in MPI, I guess you already know this from your programming assignment, but every rank like runs its own program independently. So, but you know the total number of ranks because you can get that with size. So what we need to do is first we need to get the bit that needs to be flipped because we're going to flip it to figure out where we are in this communication tree. We do the map, which is we do the mask, which is this -1. And yeah, this is the way it works. We're just going to iterate over the bits that we have from most significant to least significant. And we're just going to do basically what we had in that example, which is if my current rank and the mask is 0, and yeah, so this is saying like, are the lower bits 0 in the round that we are in? And we start, mask starts with all zeros in the lower bits except the most highest one. And then it just keeps decreasing every time by 1. And if we are, which means that we are going to be involved in the sending and receiving in this round, then we have to decide whether we're sending or receiving, and that depends on whether or not our upper bit is 1 or 0. So if rank, which is my current rank, and the flip, which is like the one in the current bit that we're investigating, is 0, which means that it was set, then I'm the sender, otherwise I'm the receiver. And you get the sender or receiver by just flipping that one bit that we're currently investigating. And then in the next round, you shift the mask and you shift the upper bit. And that's it. Yes.
I'm curious, how does it like how does the processors all know to like fix this thing like all at the same time? You know?
How did they? What do you mean? How did they know to execute at the same time? Like when you run the MPI program, they all run it at the same time. But maybe there's something. Did you mean like
No, so it's just because like the same program is running on all of them, where at each point they're expected to get this like broadcast all at the same time, and then now they're just running it at the same time.
They're not guaranteed to all start it at the same. Like if they're not all guaranteed to start it at the same time, but this is. I'll talk about it later. But with this send and this receive, you can't continue until you finish send or receive. Like especially with this receive, so nobody would go back around this loop until this receive has finished for everyone who is receiving in this round. Yes.
Can be asynchronous, right? One level, some nodes in one level do not have to wait. One level does not have to wait for the previous level to complete. Like if, say, if you can go back to
This one?
the previous one.
This one. Yeah.
So if one sends to 4, and from second to third, if one sends to 3.
Like you're saying, this one, once you finish here, one doesn't have to wait. You can just send it here.
And then 2 does not have to wait for 6 to receive it, right? 2 can just send it to 3.
Yes.
Okay, so then each level does not have to happen synchronously.
Yes, parts of the level cannot happen synchronously, but everybody has to finish here. Like the entire program is not done until all the received at the base level have finished. But yeah, theoretically, like for example, like if 0 was really fast, like once 0 sends all the data to 4, it doesn't have to wait to send the data to 2. That's true. But you are bounded by the longest path through this thing. And so this runtime analysis is still like this is like the longest path through this communication DAG in some sense. Yeah, good question. Yeah, but you could maybe free up processor 0 to do other stuff faster. Yeah, good. Yeah, so that's the code for doing broadcast. There's some assumptions here, like this used the power of 2 processors, which we don't necessarily always have. And also we're sending from root 0, which is not necessarily the case, but I'll show you how to relax those assumptions. Yeah, like I said, you don't always have this nice case. Yeah, so if P is not a power of 2, then basically we saw this trick before, like you just kind of pretend that you have more, like the next power of 2 more than you actually do have, and you just run the same algorithm. But if you just check whether or not the processor is real in the processors that you have, and if it's not, then you don't do the send or receive. But the total time and the algorithm is basically the same. Yeah, and you just ignore the ones to and from the non-existent processors. What if the root is not processor 0? One really easy way is that you could just make the root the processor 0. You have root whatever it is, and then you send it to 0, and then you just run the same algorithm. Now the root is 0, which would take an additional tau plus mu_m, because that's basically another round in this algorithm, which is maybe okay depending on what m is, but we can do better because we don't want to incur this additional. Like it doesn't hurt us in the asymptotics because log p is theta log p plus 1, but from a practical standpoint, we want to do better than that, and we can with no additional communication round. So we're going to use this broadcast tree, which is a thing that I was drawing earlier, and this is the broadcast tree from root 0, and the edges are the time step, or like the round where the communication is happening. So in round 1, 0 is sending to 4, round 2 it's sending to 2, and round 3 it's sending to 1, and then so on. Like once 4 has the data, it can send to its neighbor in round 2, which is 2 away, and then it can send everybody's 1 away in time step 3. And basically, what is going to happen is that we're going to take this broadcast tree and map it onto an arbitrary broadcast tree using bit manipulation. And it is like maybe it is easier, of course, to send it to processor 0 because you don't have to think about this bit manipulation. But the reason I want to talk about it is that later we're going to use tricks like this in embeddings to convert between layouts. So it's good to see it. Okay, so that is the broadcast tree that we had before, starting at root 0. And the goal is that we want to make this broadcast tree, but with any root. And the properties of this broadcast tree is that every root or every rank is represented once in the tree, because the data needs to get to everyone through the broadcast, and it nicely respects the hypercubic permutation, which is good because you can avoid sending and receiving from the same place, so you don't have conflicts. Okay, so in this example, we're going to make 0, 1, 1 as the root. And so 0, 1, 1 is the same place where 0, 0, 0 was. And the way that we're going to get the next thing that we're going to send it to is to do XOR using the real root rank that we actually want to use. And if you do XOR with the real root rank, we're going to get some new thing, 1, 1, 1. But we're going to get the same property that every rank is represented exactly once in this tree. That make sense? Yeah. And the reason that we do XOR with the root rank is that you can kind of think of this as like 0, 0, 0 XOR the root. And so, yes. They all respect hypercubic permutations. I guess you could, if you had an arbitrary permutation, you could, or if you had all-to-all communication, you could still do this. You might not need to do this. I guess you could think of, can you do better broadcast? I'm not sure that you can do better broadcast even if you had all-to-all communication, because you would still probably need to do like log p rounds. Yeah. Yes.
When you apply like the same operation.
Yes. Like you can you don't ever have to realize this fake or this is like it's called like the virtual broadcast tree, which is like you can always make this just based on 000, like with the bit flipping starting from the most significant bit like we had before. And basically what we want to do is we want to map a new tree called the real tree the with the real root that we actually are interested in onto we want to map between the virtual and the real tree, and we can do that with bit manipulation.
Would it just be like almost the same? So you could like write like the same algorithm, write the operation to apply the manipulation, or you like actually use the value. Is that
Yeah, pretty much. Yeah, I'll show the pseudocode later, but that's pretty much what's going to happen. We don't ever actually need to store like any of these trees anywhere. They're just like in the pseudocode that I was showing before. Like previously, we were just using rank, and rather than just using rank, we may use like rank XOR or something. Yeah, so that's how you get the first level, and then you just do the same trick for all the levels. Like you apply XOR here and here. You apply XOR with this thing, and you get this thing. And the cool thing about XOR is that it's reversible. So like if you wanted to get back, you just XOR again with the same thing. Yeah, and then with level 3, that's just, again, this thing. Like you apply XOR on all these bottom things with this thing. And so basically what is happening is you kind of run the algorithm on the virtual tree, in a sense. But before you actually do any sending or receiving, you convert the rank on the virtual tree into the true rank that you want. And then you do the send and receive. Yes, sorry, I'll fix that. Yes, exactly. Good call. So this was 001, this was 001, and XOR A is 0. Good. Questions? And so this is nice. Like this way, you can avoid an additional round of communication. Yeah, and like I said, this thing is called the virtual tree. This thing is called the real tree, and you get to the you run the algorithm on the virtual tree, and to get the actual send and receive rank, you do an XOR to get into the real tree. But there's no actually like you never actually have to store or realize the full tree. Okay, so this is the pseudocode for it. You still have flip and mask as we did before because we're going to run the algorithm on the virtual tree. Or we're going to fake run the algorithm on the virtual tree. We go through the bits again. And now you saw before this was rank and mask. Now it's just you're going to map it into the real tree, which is rank XOR root and mask. And then same here. Instead of using rank directly, we use rank XOR root to get into the real tree. And then we do the communication on the real tree. So we do 2 XORs here. And like I said, like 2 XORs will cancel out, so you can just get rid of them. So you just get rid of those excess things. And yeah, it's basically the exact same as it was before, except now, so this rank, P rank, is like the rank in the real tree. And this rank XOR root is the rank in the virtual tree. And so this is just saying like, this is doing the conditions based on your rank in the virtual tree, but you're doing the send and receive based on your rank in the actual tree. And you can see that this respects the hypercubic permutation because at every send and receive, you're sending to your neighbor in the hypercube by just flipping one single bit. Make sense? Cool. Yeah, so that is broadcast. And broadcast, broadcast is maybe like a very simple communication primitive. There are other communication primitives like reduce, which is basically the inverse of broadcast. Broadcast is like you have some data and you want to send that same data to everyone. Reduce is everybody has some data and you want to aggregate all those elements into one single piece of data. So like addition, for example, reduce comes with an operator. All reduce, rather than one rank getting the results of the reduce, all ranks get the results of the reduce. Yes. It can be implemented better than that. Like if you can, yes, of course, implement it like that, but then it would be like 2 times this. But if you remember like the algorithm that we were using for prefix sums, where you use like the full hypercube, that's how you can implement all reduce. Like when we put the total sum on everybody in the prefix sum, that's basically how this works. And then scan is the prefix sum, which is you can do it in the same number of rounds as reduce, as we showed previously by using the full hypercube. And they all have the same communication complexity, tau log p. You can get this by thinking of every level, which is tau plus mu m, and then you have log p levels, which is just log p times tau plus mu m. Yes, scan is exactly prefix sum, and you have to, like I'll show you the MPI API later, but you pass in like an operator. Yeah, so it's a good question. From a theoretical standpoint, it could be like bytes or words. I think usually bandwidth is given in like gigabytes per second, so you could convert it into gigabytes. But then there's another complication, which is like you actually truly want seconds per gigabyte because you want the whole thing to be in seconds. So you could flip. So here I'm using like notation. I'm just using mu to mean like 1 over bandwidth.
So does that mean like in the homework, for example, where we're just like saying sort of like somewhere, or not, so like 4 bytes, 1 byte.
Mhm.
Then M and U kind of just go away, like.
Yeah, this m would be 1 basically if you're measuring it in like words. M would be theta 1, so the thing would become like tau log p plus mu log p, and tau is bigger than mu. So in the theta, you could make mu go away. Yes.
So for some of these, you need all of the processors to be at the same time.
Yes, like for reduce, like every process, like the processors in the different levels need to be at the same. Like yeah, like reduce and all reduce, and even scan. I think. Oh, sorry.
So
Please go ahead.
is there like an implicit barrier when all of them are run?
Yeah, you could put a barrier at the end of each level, or at the end of each round. Go back. Maybe like here, there's no barrier because in broadcast, like we said before, broadcast is like kind of a weird case where you don't need to wait for everybody at your level to complete before you can keep going. So that's why there's no barrier here. But if you were to write a similar pseudocode for reduce, then you would need everything at your same level. So you would have to put like a synchronization to wait for everyone. And you could do that, like this is across the levels. So you just put the synchronization at the end of this 4 here. Yes.
We'll reduce with the time complexity. If you reduce at each level, then I can just you wouldn't have to add in the time.
You can reduce arbitrarily many things. Like you could reduce a vector, and then it would just be like lane-wise reduce. Like if you reduce a vector, like every processor has a vector, then at the end, let's say processor 0 is the root, then the first element that you get at the root would be the sum of all the first elements across all the vectors across the processors. So that's why they're still m. But like the reduce that we have been doing, which is you just sum up 1 element on each processor, is the special case where m is 1. But in MPI, you can do arbitrary. You also have to pass in addition to like you pass in like the operator and the type, and also you pass in like a pointer and the size of the vector as well. So then you can do like lane-wise reduce. Good question. Yeah. And same for scan and all reduce. You can do them in vectors as well. Question? Cool. So yeah, this is the code for reduce, or this is a picture for reduce. And again, this runtime is tau plus mu m at each level, and then you have log p levels. So we have log p rounds, and the way it works is that the second half sends to the left half in every round. So here, the second half starts at 4, and you send it to here. And now these two can send to here. And these two can reduce, like you can add up this data with this data and this data with this data. So the amount of data at each level is not increasing. You're just sending the partial results of the reduction here. And now this one has the sum of this one has the sum of this. And when this passes, this has the data from this as well. So now this would have this data of like this one, and this one. And so on. You compute these partial sums, and then in the final result, you just add them in the root. Yeah. And each individual processor sends or receives m bytes in each round because it can do local reduction. So it doesn't need to send double the data. That is reduce, and all reduce is similar, except everybody needs all the data, or everybody needs the full reduction. So use the full hypercube like we did for the previous prefix sum algorithm, where basically we're computing the total sum on every processor. And we did that by doing both left and right sending. In reduce, you just have to do right to left sending. Yeah, and so in this one, all processors participate in each round. So somehow the code is even easier, because if you imagine writing the code for reduce, you have to do something similar like we did in broadcast, which is like not everybody participates in every round. So you have to figure out who is doing what, when. But in all reduce, everybody's sending all the time. You just need to figure out how far your next neighbor is in the next round. And you can do that using bit manipulation again, like walking from most to least. That makes sense? So the complexity for this, even though, of course, there are more links, is the same as it was for just reduce, because even when you use the full hypercube, all the communications are happening in parallel. And there are, again, log p rounds. Okay, so are we good on that so far? So that is like the first class of primitives that I want to talk about, kind of similar to broadcast and reduce. And then the next one that I want to talk about is gather and scatter, which is another primitive. So gather it's kind of like reduce, except you're not aggregating them together. So this is a picture of what you do when you call gather. This is data, and these are processors. So in the beginning, every processor has some data that is meant to go to processor 0. Like processor 0 has A0, processor 1 has A1, processor 2 has A2, processor 3 has A3. And at the end, processor 0 gets this entire vector of data. And these are all evenly sized. Yeah, so that is gather. And one processor ends up with all the data. And an important thing is that the data has to appear in order by source processor at the end of time, or at the end of the gather. And one thing to note is that gather, like I'm talking about gather and scatter because they're important primitives that you sometimes use in algorithms. But like I was saying in previous lectures, you don't ever want to gather or scatter like the entire data, because that would just be worse than your serial time, because gathering and scattering on your entire data would be like n over p times the communication cost. So usually when you do gather and scatter, you scatter like small data relative to the size, kind of like you were doing with reduce in the homework. Like the reduction is much smaller than the total number of points that you're computing. So you do as much local computation as possible, and you just gather like kind of the end results of your local computation. And all gather is like similar to gather, except it's like reduce and all reduce is like gather to all gather, which is in all gather, every processor gets all of the data that would be for gather. Again, ordered by the source. So this is like blue, red, green, yellow, blue, red, green, yellow. This is like if you imagine your output array is out, and then your input array is in, then you index into your input array, and then count is the number of things that you gathered from each processor. So that's how you index where you're writing the in result into the out vector. Okay. So gather, the communication is very similar. This looks like reduce. The only difference is that the data is doubling in each round. So in reduce, the data was not doubling. The data was just fixed because you're doing the local reduction. However, in gather, we're exponentially increasing the data at every round, because like we can pass forward the data through the processors, but we're not doing the reduction. So the data is increasing. So the number of rounds is the same, but the total volume of data is increasing. Yeah, and another thing to be careful in gather is that you want to get the data in the correct order at the end. So you have to do some shuffling.
So you're saying reduce is more like an operation happening in this, gather is a concatenation.
Basically, yeah, exactly. Good. But it's not exactly concatenation because, like, for example, here, if you concatenate what was on 4 with 0, then it's not going to be in the right order at the end because you want like 0, 1, 2, 3. So you either have to, you either can make a full vector of size p, and then you can index directly into that vector, like you just put 4 in the middle of it, or you can keep them contiguous and do reshuffling at the end or at every level.
What differentiates all gathers then?
All gather is every all the data from all the processors is getting onto just one processor at the end. All gather is the result of this thing is getting on all the processors. Yeah, and you would do the same like the full hypercubic permutation.
What do you think to make sure that the data is ordered correctly in the
Sometimes it's important to know, like for example, one place that you might use gather is, for example, like in quicksort, like if you want to gather some result, like you pick a pivot and your data is partitioned across the processors, and you need to get some local information about how the pivot interacted with the data on the processors. You need to somehow map that information back into the index of the processors.
So like MPI wouldn't do that. Do you have to like add synchronization?
Like if you call MPI gather, it will show up, it's guaranteed to show up at the correct order. All these primitives are like if you were to implement them yourself, like in MPI, well actually, program assignment 2 will come out either today, maybe delayed to tomorrow, but then I will delay the deadline by 1 day. As an exercise, the exercise is to implement some of these primitives to get an understanding of how they work. But like when you actually write high-level programs, you can just call it MPI gather, and it's guaranteed to show up in the right order.
So like the way they implement it is by using
I will show you one way to implement it, or to implement all gather, I guess. You can do it, yeah, you can do it with synchronization, and then you may have to do reshuffling at every time. Like, for example, in the first round, this one would get 0, 4. But then in the next round, here, this has, whatever, like 2, 6. So then if you just concatenate them, you would have 0, 4, 2, 6, which is not the right order. So you may have to shuffle 2 and 4. And then again, like, then the data here again is also 3, 7. And then here, this thing is out of order as well, because this was like 2, 6. So it'd be like 2, 6, 3, 7, which is again wrong. Yes.
When you say order, do you mean like the order?
Yes. Yeah. I mean, the data should show up here in order of the ranks that they received from, or got received from. Yes. Thank you. Yeah. Questions? You could do that. The reason that it's not counted, or it's not counted in the communication cost, because you could do the reshuffling locally. And so if we're just counting the communication cost, then that wouldn't appear there. But gather would incur some additional computation to shuffle around the data. Okay. Yeah, and all gather, like I said, is basically the same communication pattern as all reduce, but the data is exponentially increasing at every level, similar to in gather. Questions? Yeah, so I'll show you an algorithm for doing in-place all gather, which is more complicated. You could map it onto an algorithm for gather as well. So the goal of this algorithm is you want to put the results of gather on every processor in order in which they received, with minimal reshuffling and as much contiguous data access as possible. So like I said, one way to do this is like, for example, let's just look at processor 0. or yeah, processor 0. Processor 0 is receiving from processor 4 in this round. You could put 0, and then you can make a vector of size p and then put like 0 and 4 in the correct indices because you know where you're receiving from, but those are far away in memory, and then like when you have to send it to the next round, like when you have to send that entire vector to the next round, you don't want to send a p-size vector. You want to send like a 2m size vector. Yeah. So you can directly index into the output array, but we want to do better because we want to minimize the data that we send in each round. You could just send the full vector with empty spaces, but that would be wasting communication. Okay. So here's how you do it. At the beginning of time, every processor has some data indexed just here by itself. So this is P0, it has data 0, like that. And in the end, we want all the processors to have all data 0 through 15 on them. And we're going to do kind of like the reverse of what we have been doing. Rather than starting at the most significant bit, we start at the least significant bit, and we pair processors together. So here, like P1 is paired with P0, P2 is paired with P3, and so on like that. And each of them is going to communicate what they have to each other. Okay. So now 0 and 1 both have data 0 and 1, 2 and 3 both have data 2 and 3, and so on like that. And you can notice that the data that they had is next to each other, like 0, 1, 2, 3, and so on. And they also are in order conveniently. And then you take the next significant bit. So now you pair, using pairing from the hypercube, we did least significant bit. Now we do second to least significant bit. So now they're 2 apart. So P0 and P2 are paired, P1 and P3 are paired, and so on like that. So now, conveniently, P0 has 0 and 1, P2 has 2 and 3, and those are also next to each other. So now the first two are going to, P0 is going to get all 4 of the first points, and so on for the first 4. And then like a similar thing happened with the next 4, and the next 4 like that. And one really nice thing about this is that they were in, like the data was next to each other. So you don't have to do the reshuffling, like I said, like the initial order was like 0 to 4. So there's some problems in the indexing. Yeah, so like that. And then we take the next step in the hypercube, rather than distance 2, now it's distance 4 away. And every pair has like the corresponding data that it needs to fill in 4 additional points. And you can see like the volume of the data is doubling every time. Yeah, so now the first 8 have the first 8 points. The last 8 have the last 8 points, and then you just do the same thing now with distance 8 apart. So everybody has all the data. Yeah. That makes sense?
So like the tree would be different, right?
Yeah, so the tree would be like here, this tree starts with distance 4 away. You basically are doing the tree in reverse. Like this is doing distance 2 away, then or distance 1 away, then distance 2, 1, 2, 4. And then the volume would also be increasing this way. Like here is downwards, like this is least significant bit pair, or most significant bit pairing. This is least significant bit pairing. And like I was saying, there's nothing special about doing most significant or least significant ordering. Like you could do either way in all of these, and you could still maintain the balance. You're just doing it backwards. And in this case, it happens that the least significant pairing is more convenient for the order.
Is that a reason all orders doesn't use the least significant one?
It can. It is less important to do so because there's no notion of like ordering in all reduce.
But was that like a reason that became the way of teaching and not the other way, or is it an arbitrary choice?
I think it's an arbitrary choice because broadcast is easier to illustrate with most significant first. But I guess maybe the thing is like depending on what primitive it is, the order in which you do the bits, one way may be more convenient than the other way. Yes.
Like we did a lot out of place like all gather and gather the data, you just place it next to where the ring came from.
Mhm.
There's like no overhead production.
So you could do that, but then the problem is like, what about in the next round? Are you going to send that entire p vector, or that vector is of length p? Yeah, like you could send that whole thing, and then in the first round, like 0 and 4 are filled in. You have a bunch of empty space. So you could send that entire empty vector, and then you could just do like vector reduce on the next round, but then you would be sending p every round. If you don't, then you are back to the same problem where you put 0 and 4 next to each other. Thank you. That makes sense? Yes.
Flexibility, like help us and tracking like at least in the last stage you said that
Uh, in the last stage you send. In the last stage you send like p over 2 m data points. Right? You start with 1, 2, and then the last one is p over 2 times m. But the number of rounds is the same as tau log p.
I guess I'm just wondering, like, would it be beneficial if you just have like each node broadcast the state of
Could you broadcast the data?
like basically like 000 would broadcast all the state of
I see, but then you would incur like p times tau m. You could, like, it would be correct to, like, from a correctness standpoint, you could just broadcast to everybody to do all gather, but then this number of rounds is log p, but if you do it with p broadcast, that would be p. Plus p. You could do the local shuffling, I guess. Like if you knew where the broadcast is coming from. Everybody could allocate a vector of length p, and then root 0 would broadcast, and then everybody would fill in the first slot, and root 1 would broadcast, and everybody would fill in the second slot, and so on like that. But then the number of rounds would be very high. Good point, though. Yeah. So I guess one thing to note for that is that it's very subtle to do this kind of thing.
I think that this is for distributed memory, right?
Yes. Yeah. There are notions of like sometimes in algorithms, just in general, like distributed or shared memory, you may want to do like a gather or a scatter. Like when we were doing radix sort last time, we did like a scatter to do the correct, or we're going to do scatter next. Let me come back to that. These primitives are for, these like analyses and primitives are for distributed memory, but sometimes in algorithms you may want to use a similar idea. Good. Okay, so that is all gather and gather. It's the same thing. The runtime is tau, which is, so the numbers we have is log p minus 1. The tau is fixed every time, and then the data size is increasing m times 2 to the I every time, and then we start I from 0. So in the first round it's m, in the second round it's 2m, and so on up until p over 2, like the series, and that is p. So the total runtime is tau log p, which is the number of rounds, times mu log p, or mu mp. And the difference, the difference was that previously for like broadcast, this was log p rather than p. Okay, so like I said, scatter is the reverse of gather. So you distribute the data from the root and you partition across the processors. So like it's different from broadcast in that broadcast, the root has one piece of data and everybody is going to get the same data. So like here, everybody got red, but in scatter, there's some different data destined for everyone. So like red is going to 0, green is going to 1, dark blue is going to 2, light blue is going to 3. So it's similar, but just more partitioning. And the message size should be much less than the input size, again, like similar to gather, for overall speed up in your entire algorithm. And scatter, the tree is very much like broadcast. But instead of broadcast, where we just sent the one data to everybody, in scatter, like we're going to share the work, but we have to send more data. Like for example, 000 has all 8 pieces of data here, and in the first round, it's going to send the second half of data onto 4, and then everybody again is going to do the same. Like this is going to send, now it has only the first half, and it's going to send the second half of the first half, which is second quarter, which is destined for this part, and so on all the way down. And it's like the inverse of gather in that the data is decreasing exponentially, but like the same similar idea. And the runtime is going to be the same because the analysis is the same as in gather. Yeah. So to summarize what we did so far, we had broadcast, reduce, all reduce, and scan, which is tau log p times mu m log p, and gather and scatter, all gather and scatter, which are tau log p mu mp. The difference is p versus log p. And when designing your algorithm, you want to use the primitive, like the least powerful primitive that you can, because often it correlates to a smaller runtime. So like, I guess in the homework, you want to reduce rather than gather. Like you could theoretically gather all your local results and aggregate them onto processor 0 and then do a summation. You could also just do that in the reduce. Yes.
You should do the scatter diagram.
Yeah, of course. So like, yeah, I could explain it again. Would it
Yeah,
help?
just the runtime part. I'm just saying, like, so why do you multiply m times p by 2?
Because here 0, 0 has m times p points in the beginning, and it's sending the second half of the points to here. So that's m times p over 2. Yeah, so it starts with everything, it sends the second half there, and then now everybody has m times p over 2 points, and then it sends the second half of that to the correct. Like it's kind of like broadcast, like you're sharing the work of doing the sending, but instead of sending one point in the most simple case of broadcast, you send, you have to distribute p points. Yep. Okay. So yeah, that is the runtimes. Yes. Sure. All right. There's one more last primitive that we're getting today, which is called all to all. And all to all is, it's sort of like all gather in a sense, but instead, okay, so you have, this is processors in Y, and this is data in X. And processor 0 has A0, right? Yeah, processor 0 has this data, like all the A data, and the processor 2 has all this data, the B data. And all to all is your it's kind of like gather, except in gather, one processor had data destined for everybody. In all to all, every processor has data destined for everybody else, and it's different data from everyone else. So it's kind of like, it's sort of like transpose. Yeah, so processor 0 has, so this is indexed like source and destination. So M00 is source 0, destination 0. M01 is source 0, destination 1. So this is going to go on processor 1. And for the other ones, for 1, this is from 1, it's going to send this message to processor 0. From 1, this is just going to stay on 1. From 1, this is going to send this message to processor 2, so on. And it's like if you have data and processors, it's a transpose of that. And so all to all is like this it's more complicated than the other ones. Looks more complicated. And in the other ones, it didn't matter whether you had a hypercubic permutation or you could do arbitrary sending because you couldn't do better. But here, you can do different algorithms depending on what permutation you have because you're doing more. Yes.
Does it only work if you put equal processes and data, or like is there a way to divide up the data?
I see. Like if the data is if you're trying to send a data different size to all the processors.
Yeah, like because you think it needs to be a square matrix, I'll just create more processes.
Yes. So you can we'll get to it in a bit. In this most simple case, all the messages are the same size. There is a version where the messages can be different size, and the size can be 0. We will get to that quickly. So for arbitrary permutations, the most simple algorithm that we could think of is we are rank I, and we have data destined for all other ranks. And so for j up to p-1, we just send our message to that processor. Is this a good algorithm? Is it efficient? Why not?
Well, I feel like, I'm not sure why not, but,
So
you know, it doesn't seem
it doesn't seem good.
Well, first that question that I can answer, but my question is like, is each cell of size n or is an entire row of size n?
Each cell is of size m.
Cells of size n. So basically, so we have so each row would be then p times m, right?
Mhm.
So that we're basically transposing a p squared times m matrix. So it would be around that time.
Yes. Yeah. So we have p squared times m data points that need to move. I guess like the diagonal doesn't need to move, but constant vector. Yes. So we have to. So the runtime is not necessarily at least p squared times m because like they could happen in parallel.
Yeah, then you just have to, I guess each diagonal can be done in parallel, I guess. Or actually, no, everything can be.
Well, this algorithm is just doing the rows in parallel in some sense. Like every row is a different processor, and yeah. So this one is doing all the rows in parallel, but it's just sending like, for example, yeah, it's just going through the different columns. Yes. You have to incur the latency every time you send to a new processor, at least once. So this would, since there are P processors, you have to incur at least. It's like one. It can be more than one element. M is like the size of the cell. You could send a vector. A second. Yes. Question?
My question is that how can we do all these in parallel? Because in the start we said that each receive and like a node can only send and receive one at a time. It cannot send and receive in parallel. Right?
Yes.
That's what we said.
Yes.
So how can we do this in parallel?
Yeah, exactly. So that is the problem with this, is that everybody is trying to send to the same place at once. So like even though this looks parallel, we're serializing the receiver. So like everybody's doing this. So in the beginning, all PI are sending to P0. And the next, all PI would be sending to P1. So did that answer your question? Or maybe it wasn't a question. Maybe it was like a runtime analysis. We're not going to do but we're not going to do analysis of this algorithm because it has the issue that you just mentioned. But there's a slight modification that we can improve, and then we will do analysis of that one. So the runtime is tau p squared because of the serialization of the sending times p squared here. So this is bad, but we can do a very small modification to fix this, which is that we just cyclic shift who we're sending to for everybody. So rather than all sending to 0 and then all sending to 1 or so on, we use our own rank to determine who to send to. And then these are all non-conflicting. So we're doing I plus j, where j is, so like in the beginning, j is 0 for everyone. But so I plus j would be I. And then, so those are non-conflicting. And then the next time it would be I plus 1 for everybody, which is also non-conflicting because everyone has different I. And the runtime for this is tau times p plus mu mp. And that, so this is higher than gather and scatter because this was tau log. The second part was the same for gather and scatter, but the first part is different. Yes.
Is this just doing it along the like diagonals, like?
Yeah.
Like,
Yeah, exactly. Like you're doing the diagonals, just moving them along.
like the bottom left to top right diagonals.
I guess you start from the main one, because in the beginning you start from I to I plus j, but j is 0 in the beginning, so that's I. You start from the main diagonal, and then you kind of like move up one, but then you have like a little bit of wraparound.
Like, I'm just saying bottom left to top right, like at a time, like each doing the next diagonal on each iteration.
Yes.
That's what it's.
Yes, that's why there's p rounds. Yes.
Will each processor receive the data in the right order here? Or do you need to do extra like
That's a good question. They will not. You need to do shifting. Yeah, because like here, processor 0, like say you have pi, you send p0 after like pn sends to that. So yeah, so you do, but you know where the source is, so you can reshuffle them. Yes. And the way you do that is just through this, using the full hypercube again. Or sorry, so that is the arbitrary, and then there's another algorithm to do it if you are limited to hypercubes. But I will get to it. There are reasons that you may prefer the hypercubic algorithm even if you have arbitrary permutations, because the runtimes are different. Okay, so to do the hypercubic permutation version, you use the full hypercube and you send half the data at each time. So this is 1/2. This is m times p over 2. And this is similar to altogether, I guess. Like you send the second half to the second half, and then the second half is responsible for distributing that data. Yeah, so like I said, let's look at P0 as an example. You start with P0, and it has its messages lined up, M00 up to M07. And in the first, every time you send away your right half, and you receive some data, which is the right half that your receiver sent you. So in the next round, you got the person that was sending to you was 4. So you get 40. They send you the first half, I guess here. If you're on the left, you send away your right half. If you're on the right, you send away your left half. And so that's why you get the left half from 4, which is 40, 41, 42, 43. And then you interleave the results in this way. So you have M00, which is what you want. You have M40, which is actually also what you want. But these 6 are not, correct? So you're going to have to give them away. And in the next round, after you do this interleaving, you again send away the second half, because that's not what you wanted. And you are keeping M00 and M40, because those are destined for you. And now in the second round, 2 is sending to you. Previously 4 was sending, now 2 is sending. So it sends you 20. So okay, these 2 are staying, M00 and 40, and you are getting, and you have these also, but you need to send them away because they're not right. But now you're getting 20 and 60 from processor 2 because those were sent from the right half. And those are also correct. Those are destined for you because those are 0. But you now need to do this reshuffling of 0, 1, and 4, 1 into the right half to send them away. And yeah, that's it. In the second half, you send the second half away, which is not stuff that is destined for 0. You receive from the right half, and now this is all the things that were destined for 0. Basically, the way this works is that the left half is sending away its right half. The right half of the processor is sending away their left half. And through this interleaving, like I outlined in red, you are shipping away the data points that are not yours. And one thing to notice is that some data points that come through you, like some things may come through you that are not destined for you. The runtime is their log p rounds. The runtime is tau log p plus mu mp, but there's an extra log p there. So this is a different runtime than the arbitrary version, and depending on the settings of M, P, and tau and M, tau and mu, sorry, you may choose different ones. Like you can analytically find out which one is better for the different settings of input sizes.
Like, say, for example, with M01 to M40, what is happening to M01?
I see. Like you're saying like what is happening to M01? So in the beginning of time, M01 needs to show up on processor 1. So it has to eventually, over time, migrate into the second half of this thing. And basically, in the interleaving, the data points that are there are, you're putting empty spaces in between the data points that are already there. And you shuffle in the ones that you received in the order that you received them. And to summarize, these are all the runtimes that we had before. Now we have all-to-all, which is, so it has 2 runtimes, one for arbitrary permutations, one for hypercubic permutations. And the runtimes are different, and they may not always, there's no like clear winner because log p is better than p, but now there's an extra factor of log p there. So it depends on the message size. I'm out of time, so I'm going to finish this next time, but we're almost done. I think this is more than enough for the programming assignment. Yes.
Going back, it just kind of doesn't seem super intuitive what Glide has. It has a better, like a faster asymptotic scatter, but they virtually look the same.
Because scatter has to send more, scatter has p data points that need to get across all the processors. But broadcast just has one that it needs to get.
Okay, I think in
One
all the
M.
examples, like, the amount of data match, like the number of processors, right?
Yeah, but in general, like it doesn't have to exactly. You could send, for example, like 2 points per processor or 3 or as many as you want.
Okay.
Yeah, but it's just like in scatter, every processor is getting something, and every processor is getting a different thing. But in broadcast, every processor is getting the same thing. Yep. Thank you. Yeah, I have to get out of here because class is done.